All right, cool. So this is my lecture day. We're going to go over some basic deep learning stuff to get Quentin and McKenna up to speed. This is going to be pretty boring for Justin. So yeah, today we're going to be talking about getting from X to Y with magic and
brute force.
alchemy.
Yes, brute force.
Getting to X to Y from magic and alchemy. So like the first thing I would probably say is that like you guys should be aware that this is going to be a pretty high, like we're going to go through a lot of stuff, but it's still going to be a pretty high overview. If you want more information and you're like interested in diving further into it, there's a course by Stanford called CS 231N. It's free, and it goes into everything in a lot of detail. They have great lectures, really great lecture notes, and it's up. The lectures are updated every year, so it has a lot of cutting edge stuff as well. This is focused primarily in computer vision stuff, but they also have one for NLP, like NLP tasks, which is natural language processing. So with that out of the way, as with the title, we're going to be talking about function approximation. And so obviously, since you all are math students, you've probably heard about a function before, or at least I hope so. Unfortunately, approximating functions and even just solving functions by hand is extremely tedious, and the more dimensions on that function, the more tedious it is by hand, if not straight impossible. And so we usually want to put these on a computer, and if you've seen any numerical analysis, you know that this ranges from extremely easy, like in the case of to extraordinarily difficult, depending on what the problem is. So like obviously like a linear function or even like a vector valued polynomial function is pretty trivial to handle on a computer. But honestly, the set of functions that we can describe using just the operations that are on a computer is generally extremely small, because after all, a computer can only do multiplication, division,
Multiply.
thank you, add,
Subtract.
thank you.
Still says
Also, as long as we're adding notes, 3 of those are verbs and 1 of those is a noun.
You guys are so mean. Nervous. So these are the built-in functions for a computer, and like obviously we can come up with an infinite number of examples of problems of functions that are defined by this, but overall these are not generally very exciting problems. And so usually the way that they'll handle this on a computer to bring in much more interesting stuff is we'll use stuff like Taylor series, for example, which obviously most people who have taken calculus have seen.
I've never seen the Taylor series.
You've never seen Taylor series? Oh boy.
Not
don't take
like
numerical analysis then.
them for like 6 weeks in analysis.
I know. So you can approximate closed form expressions of infinitely differentiable functions within an error bound that you can shrink arbitrarily, obviously. And that's pretty good, but that requires you to know that, well, first of all, be able to write down the function analytically, and to also have all orders of the derivatives at a point to be able to describe.
I'm not sure I believe that. Do you think
you don't believe that?
Prove it starting at the axioms of the real numbers?
Oh my god.
Just real quick.
Real quick.
We're gonna take that. We're gonna take that as a theorem that will be left to
Exercise to the
readers
reader.
such as you,
Yes.
Quentin. If you want, at the end of class, if you want to bring that to the board, you can.
All right, we'll have it as a short 2-hour prologue.
Okay. So essentially, the problems that we can solve with the functions that we can approximate with Taylor series are equally boring. Like they're slightly more interesting than being able to write stuff down explicitly. But still, they're limited to the fact that like it's going to take you linear time to calculate each term of the Taylor series. With numerics, you might be able to do a little better, but it still requires these weird things of like you have to know what the function is, and in general, interesting problems like, for example, what is the mapping of images to like to dog breeds, for example. I don't know if you can, Quentin, I don't know if you can write that function down. You're welcome to try that too, if you want.
What's the resolution of the image?
256 by 256. We'll go with that.
Okay, what's the ISO on the camera? How fast is the dog moving too?
You don't get to know that information.
Okay, I can do this. I need like a computer screen, and then we're gonna need to put somebody in front of the computer screen, and then that person will write
is a
down the
good
dog breed
mapping.
on a piece of paper. That is
So
a
that is-
function. You give him one
So that
image,
is
he will
in
give you
fact,
one
well,
output.
it's not a function, it's more of a function approximator. And that's kind of what I'm going to get at. So furthermore, there's a bunch of, so there are tools that let us solve types of problems that are like this, and you don't require a human sitting in front of them. And so obviously, like we know, some of these linear regression and interpolation can just take inputs and outputs and try and estimate the function based on some simple prior of like, this is a continuous smooth function that can be parameterized in X way. But usually, for example, in linear regression, given some transformation on the inputs, the data is expected to be linear. And so you're kind of hosed if that's not the case. It's the same thing with logistic regression. And interpolation is always correct about how it's going to do the inputs, but it generalizes really, really poorly. You can see that in like the Kutta phenomenon, I believe it's called. And so overall, all of these tools that we've learned about, even Fourier series, all of these are actually really terrible at solving general function approximation problems. And while they can do stuff like Fourier series can effectively encode information to be able to do like audio compression, for example, and be able to approximate the transform from a compressed space back and forth. It does that pretty well, but that's a pretty simple, that's again a pretty simple like time series problem. And so we can actually come up with a more difficult problem that none of these approaches can handle. And that's the idea that what if instead of just having a set, instead of having like X drawn from a set X and Y from a set Y, what if instead of this, we have two distributions that are drawn together and correlated in some way. They're correlated random variables. And so the values that we get, the realizations we see X and Y, the realizations X and Y are correlated enough that we could probably, like, there probably is some function that maps the expected values, but who knows? And so almost every regression, like the regression does a little better, but almost all of the approaches, the analytic approaches we've talked about so far are completely hosed by this idea, because this isn't really a proper function. A function trying to go from f of X to Y, if these are random variables, it doesn't really take on any of the properties we expect from a function, because it's a stochastic function if you want to be specific. And so we're going to talk about instead ways that we can solve this more difficult problem that in general you can describe most interesting problems in the real world as a regression problem, mapping from some distribution onto another distribution and trying to figure out what the expected value is. So we're going to do a few definitions because all of you people like math stuff. So wouldn't be a good, what is going to be a definition, a theorem? You're going to feel right at home for the beginning part of this. So the first thing that I want to talk about is, so like I said, we're going to have the domain of our approximated function be some distribution x, and the range of our function be some distribution y. We're going to call a function called the oracle. The oracle is some function f of x to y such that for all x, y in x cross y, f of x equals y. So this function is completely immune to all of the randomness. It just knows. And so the vast majority of, we're not going to do a lot of the analysis here. I'll chat about it a little bit, but I'm not going to do much of it. But there actually is formal statistical learning theory that you can talk about. And this oracle is thought of as like the perfect function for solving these problems. And usually the idea is that you want to try and bring your model, which is the next thing we'll talk about, a model or a hypothesis, as it's sometimes called, which is a function h from x to y, which maps realizations of x to an expected value, an estimated expected value of y. And we'll define h to be an element from the set of all hypotheses.
Okay,
So what's up?
sorry, just making sure I understand. We have a problem where it's just two random variables that are somehow correlated. And we're
Yes.
just going to assume that there's some perfect function that describes this relationship deterministically. And then we're going to try to approximate that function.
Yes, that's the
Okay.
idea. We couldn't possibly do it perfectly, but if we, because we assume that y is some distribution conditional on some realization of x, we can estimate the expected value, is the
But
idea
this-
at least.
Technically, isn't this the expected value of y given x equals x?
Yes. I
Okay.
mean, McKenna hasn't taken probability, so I don't want to get too specific into the like, but yes, like
How
the,
mean.
well, I'm not trying to be mean, but yeah, so it is in fact like this function is an approximation. I mean, you don't want to say expected value exactly, but it's trying to approximate y given x equals x. So yes, you're right. And so, yeah, so this is kind of how we think about what we're trying to do. We want our function to be epsilon close to the oracle, our model or hypothesis to be epsilon close to the oracle. And there's actually a lot of really interesting theory about this, which I'm not going to get into, like I said. It's pretty deep, honestly. If you're interested in getting into the really nitty gritty of all of it, there's a really good book called Understanding Machine Learning. By Shy and Shy, aka chi-squared. And they have a fantastic book on this topic. I'm kind of like skimming over like the necessary parts from the first chapter, but essentially you can actually formally talk about how good your model is. And you can prove that most some types of problems, in fact, are, you can come up with a model that's epsilon close to the oracle, even though it's being drawn from a distribution. It's called probably approximately correct learning.
Probably approximately correct learning.
Only
Yes.
that can't be the real nomenclature.
That is the real pack learning.
Probably approximately correct. If I could,
That's in fact the real nomenclature. So there's extensions that allow it to handle the distribution notation that we're talking about here. So you guys got that. So we're going to talk about a few more of the nitty-gritty definitions now that we have this idea that we want to find a model. And so we're going to kind of define some of the ways that we're going to talk about it. So we have a training set. This is kind of the way we set up our machine learning problem, is that X and Y are elements of their example distributions from that we've seen realized, where X is an element of the support. Oh God, I don't know what the nomenclature for support is. Do you know, Justin?
No.
You don't know?
No.
So it's not sup because that's supremum.
You can make it up.
That's what I'm going to do. Support X, Y are elements of the support. And these are realizations that we have observed that have been drawn from the distribution X cross Y. And so the idea is that these are sufficient information to describe the distribution, a distribution, or at least what'd you say?
Kind of a dumb question.
Go ahead.
What does it mean for it to be sufficient? Like how do you measure that?
So that's a great question. And the answer in machine learning in general does have ways to talk about this, but for the deep learning that we're going to talk about today, there is no other way than a personal hunch to decide whether or not your distribution is like your example draws from the distribution are sufficient to be able to describe the true distribution. And in fact, that's one of the reasons why in general, deep learning data sets are so huge, are because you want to be able to assume that this is in fact a representative set of realizations of this distribution, even though it's super high dimensional. And equivalently, that's one of the major weaknesses of deep learning, is that if your distribution is not well explained by your training set, then you will in fact just be hosed, and you'll probably just overfit on the data and not be able to learn anything of interest, or at least probably not interesting enough for your problem.
But also, I'm sorry. What
That's
do you
no
mean
problem.
by overfit?
So, I mean, I'll talk a bit more about that in a bit, but just like for a high level idea before we get into it later, because I will talk a little bit about that. But essentially the idea of overfitting is that you assume that your training set is representative of the true distribution, but actually it is not. So you are going to optimize to map onto from X to Y of a distribution which is not the true distribution. And so because you can assume the model or hypothesis might assume certain things about the training set distribution, it will incorrectly make assumptions I mean, it doesn't literally make assumptions, but it may, in the way that we think of it, it will incorrectly have prior beliefs that will then turn out to be false.
So it's like fitting your model fits your data perfectly, but not
Yes.
necessarily the truth.
Yes. I'm just trying to keep it inside the terminology kind of we're talking about, but you're correct. Like, I mean, it would be a good example of this is so, have you looked at interpolation before?
Yeah.
So yes, like you see that an interpolation is the perfect example of overfitting. So like if we have a bunch of points that are linearly spaced apart, this is approximately linear. Our function is clearly this, or something like that. But the way the interpolation is going to do it is it's going to perfectly get all of these, but in every place that it's not intersecting the data points, it's going to do very poorly. And that's because the interpolation assumes that it is a polynomial of this form with 0 error.
That makes sense.
So it's a perfect example of something that overfits exceptionally. And like, of course, and like just since we were talking about it, an example of underfitting would be like we have a cloud of data. And so we're just going to like assume that's approximately what's happening. And this is clearly not a sufficient function to be able to describe what's happening with this data set. So now that we have that, we'll keep going through our definition garden over here. So the training time, also known as the learning, sometimes learning phase, or like there's a bunch of training, learning, training time. There's a bunch of different ways to say it. Technically, it's the training time of the function. And so this is the period of time when whatever our learning algorithm is observes. So observes training set as a prior to produce a best hypothesis. So this is kind of the idea. So does that make sense, McKenna and Quentin?
Mm-hmm.
Okay, cool. So we're not yet, or we're not going to talk about what a learning algorithm is, but this is again, like in the general machine learning nomenclature, is that like there is some learning algorithm that we are going to perform on our training set of data to try and approximate this distribution, such that the best hypothesis goes from X to the expected value of Y.
Will we talk about what or how one would measure what the best hypothesis is?
Yes.
Okay.
Loss functions.
Yes. But we'll get there in a second. I wanted to talk about a few other things first. I mean, I guess I'll just talk about it really quick. The idea of a loss function in the like statistical learning literature is, so you have some error metric L, so the loss function is some error metric L that is defined on the set of it's on the set of hypotheses across your training set. Well, it's not the training set. It's mostly the hypotheses across the true distribution. We haven't really talked about that yet, so it makes it kind of awkward to talk about. But essentially the idea is it's like we have our set of true distribution, X, Y. This is now getting very overloaded notation. And so it goes from the set of hypotheses in the true distribution to a real number that defines how poorly you're doing. And generally the way this is defined is that the loss function should be strictly greater than 0. And it's minimized. So L minimizes when the magnitude of f for a given x minus h for a given x is as small as possible. Does that make sense? And so this is just, this magnitude here is not a great explanation. This is just an intuitive idea in the types of regression that we normally think of, but this does not have to be what a loss function generally looks like. This is just like a good example that we're pretty used to when we talk about like error in like analysis, for example. But this is not like a general loss function that every loss function looks like. It's more proper to say that like given a hypothesis space and given given a hypothesis and given a distribution, in fact, it probably would be easier to talk about this as given the set of functions where f is now our oracle. And so given this is kind of the idea of the loss function. Does that make sense, McKenna?
I think so.
And so with this, well, we're now going to jump back just because we need to get enough information in before we can do it. The test time stuff, test time, or evaluation is when it's the period of time which the model, our hypothesis, H, so H must now be our approximation for E of Y given X. And so this is essentially the idea when we are no longer allowed to learn and we must make a estimation without knowing the true label, as people sometimes say it, but the true value of Y. We must try and estimate Y given that we know X and only X. And so this is when we're actually solving our problem. Another important piece of information, the test set, similar to the training set in that it's a set of realizations. X cross Y. But in the test set, we do not allow our learning algorithm to observe this set during training time. And the idea of this is that sometimes there are, so generally what will happen when we're testing our models is that we actually do have more realizations. So we kind of want to get an idea of how well we would do at test time. And so the idea is that we evaluate on the test set and then we collect the loss, whatever our loss metric is. We take the mean loss or the maximum loss over the test set to be representative of how good, quote unquote, our model is on generalizing to the true distribution. And so the last thing that you're going to need to know last piece of nomenclature is the validation set. So again, this is a set of realizations not observed during training time directly. However, what we do let is we measure measure model performance during training with this. And so it's kind of weird when you first look at it, like what's the difference between the test set and the validation set? But so the idea is the validation set is the mock test set. It's the one that we want to try and improve our model on, because like we said, your model could overfit or underfit on the problem, and we wouldn't know unless we were able to test it on separate polls from the distribution that hopefully are also sufficient to describe the distribution. And so what we do is we actually break our test set into two sets. And so the validation set lets us, while we're training, while we're choosing parameters or model choices, we're going to only test on the validation sets that we only use the test set once. And the reason this matters is because while we're choosing models and we get back the loss on the validation set, what will happen is that you will end up in a situation where you're biasing your model over time to perform better on the test set, which we're assuming is representative of the true realizations. But if we're continuously adding bias to our model of choosing to change things to improve the test error or the test loss, you will over time start to, in a way, overfit on the test set, just based on your own changes to the model to improve it. And so when you do this, your generalization will probably be very poorly to the true distribution when you actually go to test time and evaluation, because you have biased your model saying that this test set is the true distribution. And so what we do instead is we have this validation set that we will then test on continuously, so that we only check the test set 1 or 2 times ever to get a true estimate of how well we're going to do on the true distribution. And the validation set still gives us a separate measure of how well we're doing, but without biasing our model towards the test set.
This might be getting a little ahead, but will you be showing how this works, like in terms of the gradient descent, like when you actually have like a neural network set up, like how these different sets come into play in like
Yeah,
that
we're going to
process?
code it all up.
Really?
So in the first part of the lecture, we're not going to talk about the what's it called? Give me a second. So in the first part of the lecture, we're not going to talk specifically about the validation test set splits, because we're just going to be solving a toy problem to get into like how the actual models are trained, what types, like stuff like that, and get some of the basics down. But then in the second part of the lecture, we're actually going to walk through like a real problem, and where we're going to use all of these things, introduce some other tools that are generally like the quote, for the most part, as far as I know, the best practices that you can be doing for one of these problems. So is that what you were looking to hear?
Yes,
Okay.
I think.
Also, like, feel free to like interrupt or ask me anything at any time, because I want to make sure that like you guys get the information you need. And obviously this is my estimate of what you guys think that you want to know, but I may miss things. So
I was trying to figure out how to set this up so we could raise our hands, but the documentation
just
is
interrupt me.
surprisingly sparse.
I mean, there are only 3 people attending the lecture.
I just need to be kind of fun. And
I mean,
it'll also
you
be,
could go to the chat and raise your hand that way.
can
Maybe
I
I can do
don't see
that.
the option.
You see
Oh.
me raising my hand?
I
You have to
don't.
click the
No,
you have to
you can
click
do
the
the participants.
Oh, I see it now. Yeah, I'll try my best to see that. Okay,
Oh.
yes.
Just
can.
interrupt. I mean,
yeah.
Okay, I pulled that up now. I didn't have that up before, but since I have a second monitor, I can see it now. So cool. N greater than 30. Thanks, Justin.
When everything becomes perfectly Gaussian.
I know everything's Gaussian. Every single problem ever is Gaussian with n greater than 30. That's just how it goes. If that doesn't work, try n greater than 40. So no, unfortunately, So these distributions we're talking about. So I'll just tell you, like, from my experience, the distributions of like images onto classes, for example, are so highly non-Gaussian that most of the ways that you think about these types of problems are pretty much thrown out the window. In fact, most of the use of calling these things distribution is just so that you can kind of formalize some of these ideas about how we're making mistakes and how you think about it. And oftentimes people like, for me at least, and this isn't for, I won't speak for everyone, but for me, I generally do think of it as distributions that we're learning over. It's not XY labels. And a lot of people would tell you that it is XY labels, or that's how we do this. But to me, it really is a distribution, and you're mapping between these spaces. Because otherwise you're going to run into a lot of issues, and you're going to make a lot of assumptions that aren't going to be true about real world problems. So that's my little anecdote, I guess. So we talked about the loss. We gave a super simple intro to the loss. So I guess my other thing that I wanted to bring up before we go any further into this, now that we're starting to lay some of the ideas of this, is that for most of the time, and most every problem you're ever going to be interested in solving, machine learning is not the answer. And if it is your answer, you should probably reevaluate if there are any other answers. Because
So is machine learning more so like a good check? Like if I have a theory and I've done stuff and I've gotten something, would implementing machine learning be a good way to check something you've already done?
So you could do it that way. So I guess the reason why it's hard to say that is that machine learning will really, in terms of that idea of like using it to validate, like maybe there's some sort of correlation between these two values and something, like there is some mapping that exists between these spaces that you've already done. Machine learning will give you a lot of false negatives if it is true in that world. But if it gives you a positive, like if you do have a model that works well, it does give you an idea that there is some reasonable function between those spaces, if that makes sense. So like, what'd you say?
Well, just as an example of like the lab that I work with, the way that we use machine learning is that we try to learn the electronic properties of different atomic structures. And the way you do that like rigorously, it's something called density functional theory that I don't understand at all, but I know that it's like a really expensive computation. So like one person in my group is working on, like you train it on these DFT models for like small systems, and then you try to learn how these impact when you put like a big system of atoms together that has these different features. How can you learn the electronic structure without having to do DFT, which like you can't really do on more than 100 atoms, even with like a supercomputer.
Yeah, and so one really useful thing about an approach like that is that you already know that solution exists in a way, you know? There's a lot of times when you're doing ML where you're kind of flying blind. You don't know that there is some program I could write to solve this problem. And that's kind of the reason that I'm giving this disclaimer, is that like most of the interesting problems that you want to solve can be solved programmatically. And if you can, then you should. Because like most programs are just some fancy regression computing y from some input x. And so in general, like the only times you really want to use machine learning is for one, like Quentin said, is that it's just too complex. Like the problem gets too difficult too fast to be able to solve like deterministically or however you want to do it, particularly at high dimensions. But you know that you can do it. Or when if you were to write a program, it would be too rigid in the way that it's written to be able to actually handle some of the nuance of more complex tasks that are performed by humans, for example, or animals. Tasks that we can't necessarily put our finger on and say, this is a good way of solving this problem. Those are also good candidates for deep learning. Like if you don't have any, so I guess that kind of puts a couple classes, and this isn't the only ones, but in general, these are good heuristics, is that like, if you know there's a solution, but you want to do something more efficiently, deep learning is a good way of doing it. And then also like, if the problem is one that it's a non-starter where you don't really have a way of starting to approach the problem intelligently, that's another good way to bring in machine learning. And also realize that machine learning is an enormous field. There are hundreds of different methods in machine learning that are not even related to deep learning, that are in general better than deep learning if you can use it, because they, in general, most of them will give you more solid guarantees on how well they work and if they're working well, and they can give you some indicator of if they really are understanding what you're asking them to do. And so deep learning, which is what we're learning about today, is kind of the bottom of the barrel of problem solvers. It's, in fact, I think the better way to put it is it's kind of like a bulldozer. You can solve a lot of problems with bulldozers. You should not necessarily solve those problems with bulldozers. For example,
a spider.
what'd you say?
Yes.
Yes, that is a perfect example. You can crush a spider with a bulldozer. You probably do not need to crush a spider with a bulldozer. So that's kind of my little caveat, is that deep learning is really cool. But what you're going to end up happening is when you do deep learning, you're probably going to feel unsatisfied with your results at some point, because you're going to have a feeling that, well, someone's going to come to you, as people do in businesses and research groups and whatever you're doing when you're solving real world problems, where they're going to say, this is right most of the time, maybe even almost all the time, but sometimes it's not. Can you tell me when it's going to be wrong? And so the answer with deep learning, at least right now, and there's research working on this right now, and there's a lot of honestly very interesting deep learning research on it, but the answer right now is no. I can tell you nothing as to whether or not I'm doing well or not. And there's really no good heuristic to know if one of these models is performing adequately. And so that's the reason why deep learning generally shouldn't be the first tool you pull out of your tool bag. For example, I just finished up a paper. I think I've told you guys something about it, but we learned planet pose from an onboard navigation camera on a satellite. And it performs extremely well. It outperforms all the other methods by far. And it's not really even close. I mean, it's pretty close in some places, but there's places where the other methods completely fall apart, such as like almost the entire planet is dark and you only see a very thin limb. And deep learning performs extremely well because it has a strong prior on what the center should be given, like what the parameters for this planet should be given this image, that the other methods cannot handle. And so from that perspective, it's very cool that it's able to solve this very hard like approximation problem. But then when they ask me, it's just like, hey, this is a spacecraft that costs millions of dollars. Do you have any way of telling me if you're doing poorly? And my answer is, oh no, we have no clue. I have no way of telling you if what I'm giving you is complete bogus or not. But here, like, it seems empirically to be doing well. And so that's the big caveat. And so I guess it's also really boring to hear that before you learn about this stuff, because it's actually pretty cool and pretty powerful in general. But it is important to be aware of those things, because what happens to a lot of people before they learn this stuff, once they learn this stuff, is they're like, deep learning can solve everything. And this isn't this is potentially not entirely a false statement, but there are those weaknesses. So
Well,
with that out of the
probably
way,
approximately true.
what'd you say?
Probably approximately true.
Yes. Also, if you are interested in that stuff, it's extremely interesting, and I don't want to get into it here because it's really complex. For me, at least, maybe not for other people, but for me, it's pretty deep to be able to bring into people who haven't been in machine learning stuff for a while. Excuse me. You should look up statistical learning. There's some great books. My two favorites are the Chi-Squared book that I told you about, and then also statistical learning theory. It's something like that. It's very good. That one's much less mathematically rigorous, but it does still get you on the road to understanding some of the statistical learning ideas. So that's kind of like the applied math side of deep learning and machine learning and the whole field. And then there's the other side, which is where most of the computer scientists live, which is the empirical weird side, is the most nice way that I can put that. Justin, for example, is from that side. So with that out of the way, if our problem is one of those problems where all the other methods are hosed, and there's no function approximators we have that have sufficient properties to handle the problem we want to solve, and there are no oracles, sadly, then that's when we might want to start thinking about deep learning. And so the thing that you need to start with, the reason why this is so exciting, is back in the 80s, there was a ton of research done on, neural networks in general, and a little bit of research in deep learning. The problem was there just wasn't enough computation power to be able to solve these problems at all. So a lot of the methods are old, and there is some results. There's very few results, but there are some that we can talk about neural networks, and we can talk about deep neural networks. But one of the most useful ones, and the one that we're kind of going to base every single assumption that we make on, is called the universal approximation theorem. So what's going to become really apparent in a few seconds after I've given you the really long explanation of why deep learning sucks is that neural networks are conceivably some of the most powerful function approximators that exist that we've ever come up with as humans. So let Rho, and also thank Wikipedia for this great proof.
Are you looking at Wikipedia this very moment?
I'm not looking at Wikipedia. I'm looking at my lecture notes, but I think it's fair to throw them a bone. Also note that this will be the last math you see for a while, so get comfy while you can. So let rho from R to R be a non-constant. Bounded. And continuous function. Which we're going to call the activation function. And let IM be a compact subset.
Sam, so did you go into analysis after knowing stuff like this?
I didn't know it well.
Okay.
But yes. So let IM be a compact subset of RM for any given epsilon greater than 0. And for any continuous function over IM you guys all know what this is, right?
Yeah.
Continuous function, cool. There exists an n in the naturals.
Oh my God. Sam, seriously? Like, I had never seen anything like this in my life before analysis.
In VI and BI in R and WI in RM. Where for each of these, you notice all the i's. For each of them, I is an element of the naturals, where I is less than or equal to n, such that for a function of the form f of x is equal to the sum of n I equals 1 vi rho wi transpose so for a function of this form, then
So X is also a vector of size Rm then.
so it may not be of R. I believe it is for this one, but this generalizes to spaces that aren't equal size. But
Wait, no, shouldn't it be? Because you define.
yeah, no, that's what I'm saying. It is correct.
Okay.
Let me finish it out. So
Yeah.
for all x, I guess this will help you. But I just wanted to also state that this also goes to this also generalizes to when x is not an element of IM with different conditions, but conditions that will work under here. So for all x and IM, f of x minus f of x. Remember, f of x is our lowercase f of x is our quote unquote oracle function in the set of continuous functions. This is less than epsilon. So that's pretty cool. And so essentially this is saying is that with a finite, so we're going to call this a neural network, a one-layer neural network. Because see, we have, the idea behind it is we have our inputs that then get multiplied by some weight. We add some bias as to what it should be. And then we put it through a function that decides whether or not that was a sufficient quote unquote activation. And then we reweight the outputs from the activation function to be the output of the function. And we sum that up to be the output at that, for that part of it.
So are both of our functions f just mapped to the reals?
They map to, well, I believe so for this example, yes.
Okay.
I take a small break to go to the bathroom?
Yes.
Okay, I'll be back.
So I guess I'll stop for a second then. Got any questions?
Does this generalize? We have an output of Rn, so it's more like a, general neural network.
Yes, it
Yeah.
does. But it requires more properties on the activation function.
I see.
And so I'm actually going to talk about that in a second when McKenna gets back. Not that specifically, but essentially what they did was they did a lot of these proofs with general functions, and they found out there was less to say about general activation functions. And so then people stopped really being interested in like the early days of neural networks in like the 80s and such. They stopped being interested. There wasn't any funding, so people quit doing neural networks. And even the multi-layered neural networks, which we'll also talk about. And so after people quit about this, no one made any advances in the theory. And we get to today when people start caring about it again. And it's really popular now that we can actually train these effectively. And so now they only, well, not only, I don't want to say only, but most of the proofs that I see about stuff like this, they only talk about the activation functions row that are actually being used regularly by people. And so they'll use specific functions to prove further information about it. Does that make sense?
Yeah. Is it probably just like differentiable, smooth, analytic, things of that nature?
Stuff like that, yeah.
Yeah.
Well, like realize that this actually, so actually when I look at this proof actually does generalize to Rn immediately.
Oh.
Because if you think of it, so like the output is a vector, right? Well, if you think of it as a vector valued function.
I see. So you can just like define this for every single element of the output.
Yes. And so even with just what we have here is we could define that function. And so it'd be like the projected function of the true f.
Well, but all the weights and biases and these need to be the same.
Same size.
No, like the same. Like, wait, would each WI would be the same for every single input?
So the WI would stay the same size. The only thing that could change is the n size. Because that's dependent on the function.
But I guess what I'm saying is this theorem as we have it right now doesn't guarantee that for two different functions, the VIs and the BIs and the WIs are the same.
Well, they don't have to be because you can just have a separate set for each one.
Oh, yes, you would, wouldn't you? Yes, you would. Okay. Yeah, that's how neural network works. So never mind.
Yeah, the only real issue you would have is that they'd have different n. Which I think there probably is a result. I don't have it off the top of my head, but
generalize, like take the max of n, and then you set the weights to 0 for all the n's that you didn't use.
That are yes, and it all has the same input information, so there's no problem with not being sufficient information to predict the f of x, the projected f of x function for the Rn case. McKenna, you're back.
I am back. We can continue.
Cool. So Quentin and I just ascertained that this actually immediately generalizes to Rn as an output space. Because you can define you have a set of n f of x, like big capital F of x's, and the projected f of x, lowercase f of x's. And so just because they have the same number of inputs for all, they have all the information as the inputs for all of them, you could construct a vector valued function using this to go from Rm to Rn.
So instead, your f at x would simply be an element in a vector.
Yeah.
Okay.
So this is cool. And this is extremely useful because notice how we say any continuous function. We don't have to know what we don't necessarily in here, like we kind of assume that we're going to do well with an epsilon close. But there's nothing here that says we have to know f. We need properties of f. All we know is that we can get epsilon close with some set that is not connected with f directly. And so an extension to this that's also really useful, because there is a worry here. It says that there exists an n such that this is wide enough. But that could be unreasonably large. N could conceivably be completely unbounded. Well, unbounded. It is bounded, but it could be above what our computer can do. So it's not quite clear yet that this is useful. But actually there are extensions to this, which I'm not going to write down explicitly here. But essentially there's an extension to this that says that if we compose sequences, so we have like an F1 and an F2 of x instead, if we compose a sequence of these, then we can actually put an upper bound on the width proportional to the size of m, r, well, so m in R of m. And this is fantastic because this means that we can build reasonably sized models without it growing too quickly. One of the requirements for this to work is that our row needs to be nonlinear. So remember, a row of x, this needs to be nonlinear.
Why?
It's just a part of the proof that they do. I don't have it written down in front of me right now. It is a good question though.
Also, then your function really would just be linear. So, and the composition of all of them would be linear.
Oh, that's actually a good point. If you were to compose these, you could simplify it into, that's actually completely true. So that's one of the other reasons why it should be nonlinear. I didn't even connect that to this proof. Thank you, Justin. But in general, the other reason why you use a nonlinear activation function is because you can think about f as a matrix operation on x. And so if you were to apply them successively, this would end up being one matrix. Like it would just simplify into one matrix. And then it would just be a linear model with biases. And so the nonlinearity allows us to do a much more complex function with much less. It's known as the expressiveness of your neural network. Is the depth, it increases the expressiveness of it. So yeah, that's our quick little dive into the math behind it. So we kind of, basically what happens in deep learning at this point is we say, this sounds fantastic. I am never going to do math again. Because this is enough. There's something that exists. And if we could ever find it, or even something close to it, it's going to be great. And so we're going to have a couple more definitions, but I'm going to switch over to my Jupyter notebook now. So I'm just going to drop these in here. You don't have to type anything in yet. I'm just going to use this for my presentation. So first I thought I'd show you what a neural network looks like. This is why I didn't use dark theme. There we go.
Okay.
Surprise! It's all here. So on the left, this is our our normal f that we talked about. That was that first function.
Did we lose him again?
I think so.
What'd you say,
Still hear
Quentin?
him typing. It's kind of weird, right?
Can you hear me?
So
Why is this dying?
Oh, there he is.
Okay, you hear me again?
Yes.
Let me see if this helps. Okay. Is that better now?
Yep.
Okay. Linux is a stable and useful operating system. So anyway, what we were talking about before was we essentially said that there was some n, which would be the number of nodes here. You see my mouse when I point towards things?
Yeah.
Okay, good. So there's some n here. Oh my God. Calm yourself, computer. Such that there's enough that we can approximate any function. However, the idea of function composition there ends up with something that looks like this. And so that's the idea of deep learning, quote unquote, right?
I have a problem with this figure. If you notice the top layer of neurons, they're only connected between the first and second layer, and they neglect that line between the second and third and fourth.
You know what? You're right. It's completely, we're hosed. We can't even talk about anything anymore.
Well, this has been a fun lecture. I'll see you guys next week.
So now that we're going to ignore that, it's true. This is not my figure. I got this off Medium. Someone had a good talk about this. The link's here if you ever want to look at it. Actually, don't think the original blog post with this in it even exists anymore, but it's been passed around so many times that this is just like the canonical, this is a neural network. So anyway, back to what I was saying, back on topic. As I said, these are neural networks. And these are just the deep neural networks are just the composition of a selection of them. And so the reason they're called neural networks, just so people know, McKenna, you're not like super a biologist, but most biologists get really pissed off here when we're just like, this is a neural network. This is what brains look like. And so the reason it's called a neural network is because it is inspired by the interconnected nature of naturally occurring human brains, as well as nonlinear activation functions, which are strikingly similar to how a neuron decides whether or not to fire to its neighbors.
So you're saying it's exactly a brain?
It is inspired by.
Exactly.
But a lot less powerful, Dan.
Yes. Well, okay, so I'm side tangent. The reason why, some of the reasons that you can't explicitly say that they're the same is because the human brain, for example, has a bunch of things that are specialized at solving certain problems. This is like a general inference model, which again is not exactly like how the human brain works, Quentin, but but there is much more specific ways that the brain works, and it also has stuff like memory, which we don't have a concept of here. However, with that said, there are parts of the human brain and in general brains that can be well thought of as having this structure. For example, the visual cortex works similarly with much more complex parts to it, such as attention mechanisms and other stuff that I won't go into. But once you get past the disclaimer that this is not a human brain, this looks a lot like what, to people who aren't biologists, what they would think a human brain is. And as far as some of the things that we see empirically, from neural networks, this is probably a better model for how brains work than whatever the neurologists are doing. So that will definitely piss some people off.
That's a good thing I don't do anything involving neurology.
I've been to lectures before. It's really common. So if you give a lecture like this to the public, a neuroscientist will come and say, this isn't how brains work. This shouldn't be called a neural network. I know because I've seen it happen to every single one that I've ever been to. Every single neural network talk I've ever been to, that someone stands up and there's like, this is not how the brain works. And they're like, I never said it was.
Yeah,
This
real
works
neural
pretty well."
networks have differential equations and stupid stuff.
So right here, these are just a few terms. You don't have to write them down. I'm just going to use these terms exclusively to describe things for the rest of the lecture. So I want to have these written down.
You don't have to write them down, but
Not written down.
So back up to, oh crap, it's not here. Well, hold up. I can actually copy paste our theorem into here. Look at that from the notes. That's what math feels like.
So do you have a app that converts written stuff into handwritten stuff into text? How are you
No,
doing?
I wish I did, but we could do that. Like we could do that with deep learning. That's
Oh
why
my
that.
god, you literally what?
Now the snake has eaten its own tail now.
You did this in
Why did-
late?
What'd you say?
You teched this up?
Yeah.
Oh my god.
So anyway, so we're going to talk through a couple of these ideas. So the weights of a neuron. Now that so first of all, we fully come full circle of pissing off the biologists. We're going to call these neurons. Our disclaimers out there. These are all neurons. They're interconnected with one another. These are the edges between the neurons. That's how real brains work, obviously.
You should have called them synapses.
Synapses. Okay, so anyway, so the weights of a neuron is going to be our WI vector. The B is going to be known as the bias of a neuron. We talk about the parameters of the network as the weights and biases, or we just call them the parameters. A layer is one function application. Where's it going? Oh my God, Quentin.
What?
Oh, I just got a message from you from
What?
like 20 minutes ago.
I haven't sent
So
anything.
anyway, this is what happens when you give a lecture in the middle of an apocalypse. Everything's falling apart. So this is a layer. This is an input layer. This is an output layer. This is a hidden layer. Hidden layer is just a layer that cannot be seen, that does not have a direct application onto the input or the output. Generally, the input layer is going to do some sort of pre-processing on our data to make it easier to solve these problems. And the output layer is going to have some post-processing to make something meaningful of all the crap that we just talked about. This type of layers that we've talked about so far is called a linear layer, probably because it is one of those matrix multiplications with biases, with a nonlinearity attached to them, the activation function. So each of these layers would be a linear layer, and almost always a linear layer has an activation function associated with it, even though it's called a linear layer, which makes it completely nonlinear. And so, yeah, this is a deep neural network. You can now decipher that. This is not going to take over the world, probably. This is a bunch of matrix multiplications. It's been around for a while. And so, yeah, so that's basically, I think that's most of the nomenclature. We'll just need to talk about these types of problems when we're coding it up. The only other thing, there's a couple other things we actually need to deal with before we get to write code. And so for one of them, that you may know, a studious student may notice that not all problems are regression problems. But I would actually fundamentally disagree with this. Does this to you look like a regression problem or a classification problem? I want to pick lines such that everything on one side of the line is something. This is, by the way, an approximation of the distribution of image space.
Are you telling me that chickens aren't deers?
So the idea here that I kind of wanted to get at is that we can kind of there's a large part, I wouldn't say most, but a large part of deep learning is figuring out how to pose a problem that's inherently not a regression problem at all and try and talk about it as a regression problem. And so like you can kind of see here, like how we have this idea of like, this is clearly a regression problem saying is not car, you know, is not deer, is not airplane, based on which side of the line it's on. And so we're going to try and make classifiers like this and a bunch of other problems. We're not probably going to deal with them today, but a bunch of other problems, this whole idea.
That everything on the inside of the triangle are equivalent?
So that's not necessarily true. It just means that they are not in any of those sets.
Not airplanes, not deers, not cars.
So it's
like a chicken is
your
that.
classic cats, chickens, boats.
Fire trucks.
Yeah, wait, how's a fire truck not a car? I think
it's close. If you notice, it's close in image space, but not quite a car.
I think the chickens should be closer to the airplanes.
Yeah, actually, that is true. How's the cat? The cats and the chickens should be switched because the cat is definitely closer to a car.
As I said, this is an approximate embedding.
And the toads should definitely be closer to the boats.
Artist depiction.
So I'd like to note that this is not mine. This is from that really good Stanford course I talked to you about. So leave any comments you have for them about the poor quality of this image space representation. I think it does a good job, though, to explain kind of how we're going to think about classification, for example, because that's one of the problems we're going to look at. In fact, I think that's the problem we're going to look at for both parts of this lecture today. I didn't have time to prepare the third part. So, and I also thought you guys were going to get bored. So yeah, we've been able to pose, using this type of an idea, we're able to pose classification as a regression problem, regression problems as a regression problem. We can probably come up with some sort of loss function that defines this, but in general, as long as you can pose a loss function to be able to, a differentiable loss function for at least what we're doing here, but in general, a loss function for machine learning that defines like how well something is classified or not, or whatever the regression problem it is, it turns it into a regression problem because you can just regress to a smaller loss on your hypothesis. And so most of what we're doing is trying to talk about how can we turn these into regression problems that are feasible to learn and what functions are good at approximating these weird regression problems. Another example of regression problem, for example, would be like, I have an image, for example, and within the image, I want to be able to pick out where the cat is in this image. So I want you to draw a box around the cat. And so the regression problem is then, I want you to output an X and Y for the top left corner, and then the width and the height of the box. And so that is, again, a regression problem. But the actual output, the problem that solves, is extremely different because now we're doing object detection within images. And there's a really cool paper on that called YOLO. And there's a bunch of other papers on it, but YOLO is the popular one. Mask RCNN is a really good one that I think I prefer more. But nonetheless, YOLO is way more popular. And so stuff like this is basically that type of a problem. And so in general, we're going to call this whole field where we live in nonlinear functions and these nonlinear function approximators, deep learning. And then we're also going to inherit all of the problems of deep learning. For one, and as you said earlier, there was a good question of how can we find a hypothesis. There's no promise that we can, in fact, find this F. It's really sad. There's no promise that we can do that. There's no promise, no proof, no anything that we can say as the feasibility of the learning problem that we're posing ahead of time. And that's problematic, but that's the result of being able to work in these really complex nonlinear function spaces. So again, this is kind of why I was saying that if there's any other method than deep learning you can use, you probably should. Because, I mean, it's not a very comforting thought to know, so like, is this possible when you start out? And the answer is no idea. There's no way to know, except to do it. And then even if you do it, you may not know if it's possible. Or possible to do at the level that you want to be doing it at. So the reason that I wanted to talk about all this in terms of distributions is that it gives you a better intuition overall in when things are going wrong, because we have no theory to back it up. And that's not to say there's never any theory in deep learning, but when we don't have theory, you're going to have to go with your gut and your experience a lot of the time. And so, with all of that said, we can write our first line of code.
Whoa.
So, I'm going to need you guys to go into your computer. So, do you guys have your Jupyter Notebook up?
Yep, I do.
So the first thing I want you to type in at the top is this. And so these are called magic commands in Jupyter.
Wait, hold on. I have a folder. I need to actually create the notebook.
Okay, no problem. I can wait. I can kind of explain.
Torch.
What'd you say?
What about the import torch?
You can just
command?
get rid of that.
So can I go into my terminal and then just like create a new file called something.ipynb?
So the way you're going to want to do it, I can show you really quick. So we'll open up.
I'm not familiar with Jupyter.
No problem. Did you open up the conda? Well, do you have your environment open? So your bash.
Yeah, I did. Now I do. Yeah.
Type Jupyter.
I mean,
space notebook.
I have Jupyter Notebook up in the web right now. I just don't.
Then open it. So what you're going to want to do then is when you get to, so it's in the web. I don't want to open this for myself, but you open it in the web, and then you're just going to hit, there should be a make new notebook option.
I'm sure there is.
Let me find it. You do not want a lab. So if you click on, like, say, workspace, then you can click new.
Yep.
And then you can click Python 3.
Oh, okay, I see.
And that should bring you to here.
Yep, that's where I'm at. Okay.
Cool. So I'm actually going to get rid of this to make it easier for you guys. Do you guys have all this information in your heads written down somewhere?
More or less.
Good. It's gone forever now. All right, so the first thing we're going to do is everyone in a Jupyter Notebook. Justin's probably not in a Jupyter Notebook.
In a Jupyter Notebook. You're
Right,
probably
so-
going to hear me type a lot.
So we're going to use what's called a magic command at the top of our file. And I have,
Cars are both airplanes and deer.
Ignore that.
just saw that. Very funny.
All right, do you guys see me typing, by the way?
Mhm.
Okay, cool.
Should
So
we
these are
also
called,
be typing this?
what's up?
Should we be typing this as well?
Yes, so I restarted my Python notebook, so I have the exact same Python notebook you do right now. It's completely empty, nothing's ever been run. So you're gonna wanna type these in. These are called magic commands, like I was saying earlier. These are built into Jupyter themselves. And the idea behind these, is, the reason we're using this specifically is because it allows us to reload Python modules on the fly without restarting Jupyter Notebook. Because I kind of anticipate that you guys might not have all of the dependencies installed. And so you're going to be able to get any dependencies from your Jupyter Notebook while we're working without having to close out and open it again, as long as you run this first. But it has to be ran before anything else. If you didn't run it first, make sure to restart your kernel, Quentin.
I ran it.
Okay, you ran this before import torch.
Yes.
Okay, good. Awesome. So then the other things we're going to grab really quick. Import matplotlib, pyplot, plot. This is your go-to plotting solution in Python, Quentin, since you're not used to Python. Did you end up taking an intro to Python course this week?
No.
That's all right. This is gonna get real spicy for you. So, luckily you just have to type what I write. So we're also gonna import numpy. It just means that I have to explain to you what it is. Numpy is numerical Python, and it's also really powerful. So once you have these, to be able to execute a command, you hold down Shift and hit Enter.
Well, I know how a Jupyter Notebook works.
Okay, good. Well, I didn't know if McKenna knew either. I'm just for the holistic.
No, that was useful. I appreciated that.
So you want to execute both of these lines, and so you shouldn't see any errors at this point. And if you do, let me know. And so now we can import the fun stuff. So our first step into the world of neural networks, import torch. Import torch.nn as nn. I'll let you extrapolate what nn means. So you should be able to shift enter that again, and nothing bad should happen as long as your PyTorch is installed correctly. Is that big enough, by the way?
Yeah, that's perfect.
Okay, good.
And I have a dumb question that you've probably already answered.
There's no dumb questions.
What is the library torch? Like, what is it? Is it like a deep learning library?
So PyTorch, so I'll talk about it really quick. It's a good idea. So PyTorch is a deep learning library, but I think that's kind of undersells what it is.
Okay.
I wish they had a good
I thought that
explanation of what they do.
TensorFlow was like.
What'd you say?
I thought TensorFlow was like the main Python library that did the neural networks.
So this is actually what I was going to get in next once everyone got it imported. So Torch is short for PyTorch. And for me personally, it's my favorite deep learning framework. The technical definition of it is a tensor library for GPUs and CPUs. That is to be able to do n-dimensional matrices. So like basically the generalization of a matrix past just the two-dimensional directions on GPUs and CPUs. What I was going to make sure I said was that calling what it does tensor operations is quite a stretch, which bothers physicists such as McKenna. It's not doing real tensor operations. It's computer scientists like to think of themselves as fancy. And this is kind of where we're starting with that. We use big words. Essentially what PyTorch is is it implements a bunch of numerical operations, which are really commonly used for deep learning, on the GPU extremely efficiently. And then it makes the interface available through Python, so it's really easy to write. It's not the only deep learning framework in the world. Keras is a really good one. It uses TensorFlow as a backend, which is what you were saying earlier, Quentin, TensorFlow. And that's all made by Google. With Keras, with TensorFlow, is directly comparable to PyTorch. And in fact, TensorFlow often has much better tools for scaling deep learning operations, as well as sometimes having faster operations depending on what it's doing. There are things. What'd you say? What'd you say?
I can't stop reading my troll cat messages.
Thank you, Justin. Essentially, there's things which both of them can do that the other ones can't. It's kind of beyond the scope of this tutorial, but the sufficient information is that if you're an individual researcher or talking to anyone in academia, you're going to use PyTorch. If you're developing deep learning systems for a company, or you have an obscene amount of resources, i.e. Google or Amazon, you should use TensorFlow and Keras. I personally am not Google or Amazon, so I'm going to be using PyTorch. Note that there are tons of people who choose to use TensorFlow. If you want to, I'll laugh at you a little bit, but you can. And we won't be talking about it in this tutorial. Most of the things transfer over. One thing you'll find when you're doing PyTorch as opposed to TensorFlow is PyTorch makes sense a lot of the time. And that's not even a dig. It's just, if you, so like, let's say you have an error in your code. In TensorFlow, it's going to give you a huge stack trace, which is extremely difficult to understand. And oftentimes it's almost impossible to decipher it. At least for me, that's just me. There are people who can decipher it. Maybe Quentin's one of them. But if you have an error in PyTorch, usually it will be like, hey, this is the part of your code that didn't work right. Maybe you meant to do this. And that is that's way easier for me when I can't hire 100 machine learning engineers from Stanford to do my work for me. So does that answer your questions, Quentin?
Yes.
So I'm going to further sell you on PyTorch as we go through this. But we're going to get back to trying to do stuff interesting. So the NN part of this is the neural networks module of PyTorch. And that's kind of why I like to say that there is a distinction. PyTorch by itself is not a deep learning framework, but almost certainly NN is the deep learning framework within PyTorch. And as an extension, NN.functional is is a collection of functions that we're probably going to be using. It basically exposes you to a lot of really commonly used functions baked in and made efficient by PyTorch, which aren't necessarily directly, don't have weights or biases or something like that. So a good example would be like your activation functions will be in functional. Does that make sense?
Mm-hmm.
So let's make some data. Once everyone's all ready and stuff. So let's put together some parameters of stuff that we want to, not as to be confused with parameters of a neural network, but these are just, we're going to put together a data set, a classification data set, just to try and figure out how we can do this. So we're just coming up with some constants. You can change these if you want, as long as you keep using the names of them, like these variables. You shouldn't have any problem with using different sizes and experimenting with it. So we're going to create our data matrix, which is going to be a set of one, oh God. So we have our dimensionality times the number of different classes and points per class. Basically, each row of this matrix is going to be a single example. Does that make sense?
Example of
and
what?
What'd you say?
You said each row will be an example. And
So each row will be one data point. And so we're going to populate this in a second, but we're also going to need to give labels to each of these. And the reason this is n by k is it's just like there's n data points per class. There are 4 classes, and each data point has a dimensionality of 2. This is just the numpy function for creating a 0, like a n-dimensional matrix of zeros. And so we're going to do that as well for the classes. Let me know when you guys are caught up to me. And you don't have to write the comments if you don't want to.
I think they're useful.
Yeah, there's no way I'll be able to come back and look at this code and have any idea what it's doing without these.
So you'll notice that in the second zeros, we also have this d-type parameter.
Mm-hmm.
This is just saying that we want the numpy array. So numpy is also, so like I said, almost all this stuff with numpy and PyTorch is hiding C++ code that's very fast at what it does, to make it easy for people like us to be able to do this efficiently, like to make science easy instead of hard, by using it inside of Python. But there still is the realism that it's like C++ on the underside. And so stuff like this d-type, uint 8, we're just saying that we want this numpy array to be a bunch of integers, 8 8-byte integers, I believe. It's not 8-byte.
8
Is it 8
bits, isn't it?
8 bits? Yes, you're correct.
Because 8 bytes would
Unsigned
be
8-bit
gigantic.
integer. It's 1 byte.
Yeah.
I just want to give you guys the right info. So, and we have one label for each of our data points. Are you guys all good?
Mm-hmm.
Okay, so let's populate our data. So, and this data generation code is from that Stanford course, because I didn't want to write the data generation code myself. It was very painful.
Does that say IX?
Where? Yes.
Yes.
I'll talk you through it in a second. So we're just making a parametric weird spirally thingy is what we're trying to do. And so what we're going to do is we're going to create a range of x indices for each one. So we know there's n indices, and so we're going to create a range so that iterates over all of them. So we can index into our matrix, our x matrix and our y matrix. So this is probably even better said IDX, but the stuff they used originally was IX, so I'll keep it consistent. And so this is our indices that we want to access, because we're going to, one thing that NumPy and PyTorch both support is the ability, well, this is a very MATLAB-like function, the ability to operate on a bunch of things simultaneously, or at least do a computation in parallel by selecting a range of indices and then modifying things in parallel. it did originally, that actually did originally come from MATLAB. And something you might notice, Quentin, is that NumPy's interface is actually very similar at times to MATLAB.
Yeah, linspace and zeros and random are just MATLAB functions. So
Yes.
what you're saying, if I'm hearing it correctly, is that MATLAB is better.
Better?
Correct, right?
MATLAB doesn't have PyTorch.
Correct. Okay, so I think we're saying the same thing.
But I thought I would give you that, is that they wanted to make it as easy as possible for people to leave MATLAB and come to Python. And so they copied all of their interfaces and made them faster. So we're now going to update these values at each of these indices by pairing these. And then we're going to do this as well for the outputs. I actually was supposed to make this lowercase, but I'll make it uppercase from now on.
What does the .c do? Sorry.
I don't remember off the top of my head, but I can look it up really quick. I remembered when I was writing the code. If that helps you at all, like a week ago.
I mean, I'm sure it's there for a good reason. But
Oh, it's just concatenate.
Oh, okay.
Oh,
That makes sense.
So we're concatenating these sequences together along a axis so that we can make these the X and then the Y. And then we're going to give it everything within this range is going to have the class ID that we're in right now. So this assigns the X and the Y of the data point and then the class that it's supposed to have. So now we should visualize this. What's up?
I've never seen that np.c thing, but that's a very R thing.
Yeah,
R
I
has
agree with
the
that.
C is the concatenate function in R. But anyways,
so are you guys all caught up?
Mhm.
yeah.
Okay. Visualizing the data. So we're going to visualize this. I'm actually going to increase my DPI. You can change your DPI to whatever you want. Just keep it over like 125 so that it doesn't become extremely small figures. But if it's too big, it'll slow down your computer.
Do you not have to terminate the for loop?
What'd you say?
Do you not have to terminate the for loop?
No, that's a Python thing. You would know that if you would have taken a Python course.
So it just knows based off the indentation?
Yep.
Uses the indentations.
That's kind of cool, I guess.
Right. And then once we have all this, oh, I didn't write mine correctly. Oh no, what did I do?
No, that means we all made the same mistake.
I'm an idiot. Ta-da! We fixed it. All right, tell me when you guys fix this. It was just a couple mistyped things here.
Oh, C equals Y. What is C?
Syntax
It's a
error
class label.
for J,
Class label.
range of K. Oh, I need a colon after range of K. Come on, son.
And just so you know, Quentin, for your like knowledge here, is that this colon operates over all of the indices. So this is what we get from that.
Yep.
This is our data set, and this is what we want to classify. So I would argue, and maybe I'm wrong, maybe Quentin can find something for this, but I don't think there's any linear function that separates these classes.
Just real quick, could you go back up to the code because I'm not
Yeah,
getting
no
that.
problem. I just want to show you guys what we have.
0, x, y.
My bad. That was my bad. I'm new to this typing and talking at the same time.
So mine does not look like that.
Mine does look like that.
Mine does look like that as well.
Mine too, Quentin.
Okay. If you promise not to mock me, I can share my screen.
Here, I'll just send you the code over the chat. There you go. Get you back up
Sam
to speed.
can't guarantee he won't be mean to Quentin if he screen shares.
What'd you say?
Can you not guarantee that you wouldn't be mean to Quentin if you were to screen share? Is that what you're getting him to
It's
code?
more like this is the longest that my screen share has been working without interruption.
Ah,
And so I'm trying to keep on that. So Quentin, did you get the
It's different.
code that I sent you?
Yes, but why?
You're gonna have to add tabs.
No, it came with tabs.
Oh, cool.
But what is the difference?
also, Quentin, our complex exam scores are in.
Oh no, interlude.
So any luck, Quentin?
Yes, your code seems to work, but I stipulate that it's the same as mine. And I don't know where the problem is.
But wait, did you paste my code into your Jupyter notebook and it works, but yours doesn't work?
Yes, mine does not work.
Then it is likely not the same code.
I'm not sure I accept this. I think
So now that Quentin has that, so this is a clearly non-linearly separable set. And in fact, like just because of how weird it is, I think it'd also be pretty difficult to come up with a kernel for a linear classifier, even if you really pulled out all the stops to really use like an SVM or something, which is something most of you don't know about. Justin, for example, knows. I think it would be challenging to classify this data set using most methods, other than like, I don't know, MS Paint by a person. So so once Quentin's up to speed, waiting on Quentin.
oh, that's not so bad.
Wait, can I add text?
Yes. So go up to, you're in Jupyter Notebook, right?
Yep.
So you'd be able to click on a cell, and somewhere there should be something that lets you pick between code and markdown.
Oh.
You can also
that's
just
really nice.
if you're selecting the cell where it's like blue and your text is not in there, you can press M to do markdown or Y to do code.
Oh, I didn't know that.
Wait, can you say that again, Justin?
So if if you have like a blue thing selecting the cell, but your text is like, if your text cursor is in there, like it's going to be green, but if you just click outside of it, it'll be blue. Then you can just press Y to switch it to code, or M to switch it to markdown.
Oh, that's awesome. Thank you.
I have discovered the bug in my code.
What was your bug?
It's not important.
Blow my nose.
It would be really funny if we could still hear Sam blowing his nose from Justin's screen.
I heard it.
All right.
Couldn't hear it, but
So does everyone have a data set?
Yes.
So now we're going to use one of the strongest parts of PyTorch, particularly when compared to, what's it called? TensorFlow. And that's the class syntax of being able to write a neural network. So if you knew Python, this is going to be really, really easy. If not, then I don't see if this will be any better for you, but you'll know it now. So what we're going to do to be able to write a classifier on a neural network, so we're going to say class Oh, this is now marked down. Just like, where's my syntax highlighting? So class, simple classifier, and then nn.module. And this is just saying we'd like to create a class named simple classifier that inherits from all the properties of the NN module.
Also, you wrote simple classifier.
Thank you.
Yep.
So then we're going to define the member functions. So we're going to do our initialization function, which takes in the class itself and the number of classes we want to discriminate from. So first let's initialize the PyTorch stuff. And also, just so you know, once you've started to type something out in Jupyter, you can hit tab to complete it.
Oh, that's nice. I didn't know it had an autocomplete.
So in general, and I'll just say this is like, in general, Jupyter notebooks are really good for doing experimenting. Like when you're actually running like a big, so like in this stuff, when you're running a really long-term training or something, they're really unstable. But when you're just experimenting with code or like trying to come up with a model or trying to visualize data, Jupyter notebooks are really good because they're kind of interrogative, you know, interrogative, is that the correct way of saying that? It's like you can ask it a question about what you're doing and it will give you an answer. And so generally I do a lot of my like Python prototyping in Jupyter Notebook, and then I'll transfer it into a normal Python script for long execution after I've proven the concept. So we're also, to finish off this call, we're going to call the init function. Can you guys see my Teams messages?
Yes.
Yes, okay. Status, do not disturb.
Sends you a message. It's like, do not talk to me.
What message?
What'd you say?
What message?
Nothing
Exactly.
to see here. Move along. So first we're going to do that initialization. This just initializes all the NN module stuff. And this is just saying I'm going to call the parent class's init function, which is NN module. And then we're going to fill up our matrices. We want a 2x10 matrix that takes in our 2 coordinates, and we want to give it 10 values. And then we're going to have a couple hidden layers. And this is the syntax for getting a linear layer in PyTorch, is you just say nn dot linear and then the shape. It's the input and then the output. And this is how, that's actually how most of the things are defined in PyTorch, is like you set up your input size, you set up your output size, you maybe set up a couple of extra parameters that are important to that specific type of a layer. And you just have to call the nn dot whatever the thing is, and then it will create a function. That's
So
what that's
here,
doing. Is,
are we kind of just creating private variables of the class?
I mean, yeah, that's what we're doing, but they're not private. We can look at them whenever we want.
Okay.
It's a downside of Python. So we create another one of these hidden layers, and then we're finally going to create our output layer. This is exactly like the picture we were looking at earlier. So this is just saying that we take in 2, we put it up into 10, then we go from 10 to 10, 10 to 10, and then 10 to the number of classes. this doesn't actually tell us anything about how the neural network, we haven't told it enough information about how to actually make the neural network run. We've just instantiated a bunch of layers. So we're going to define this function called the forward function. And this is the actual forward propagation, which is how we talk about like moving through the layers sequentially. The actual composition of the functions applied to a variable is called the forward propagation. And so we're going to say x. So we take an input x. X is equal to f dot ReLU. Note that, remember how earlier we talked about the functional library, right? So the function, the ReLU function, the ReLU, I'll just give you a quick aside really quick as to what the ReLU is. The ReLU is also known as the rectified linear unit, which is usually written as like ReLU. And it's just a function. It's a super simple function. It's just, so before I do this, if you were to ask for a continuous function that has a nonlinearity, how simple of a nonlinear function could you write down?
X squared.
That's pretty complex.
Maybe for you.
I would argue that we should pick something that is as simple as possible, as close to what linear is. And that's what a ReLU is. A ReLU just takes the maximum between x and 0. It doesn't get any more simple than that. This is in fact nonlinear if you want to inspect it. Let me make this a little smaller. It's easier to read. This is the ReLU function.
Can you go
It's
back
0.
up a tiny bit? Sorry. I
Sorry.
was distracted by Justin's comments.
I don't see what's so funny.
You don't need this code. And I'm going to get rid of it in a second. I just want you guys to see, this is all it is. A ReLU is just, it's linear when it's greater than 0, and it's 0 when it's less than 0.
Didn't we need the activation to be bounded?
Yes, we're just going to assume that we're working on a finite, like a finite range, which actually ends up being something that we can talk about in the next part of the lecture if you want to. So remind me and bring that up in the end of at the end of this part of the lecture, okay?
Okay.
So I don't forget. In fact, I'll write that down right here. Quentin's comment.
I'm going to the bathroom.
Cool. So it's pretty simple. If we just ignore the fact that it doesn't satisfy the properties we've talked about so far, it's great. They actually have done all of the other, so all the theorems we talked about, they've also proven them with ReLUs, even though they're not bounded. Because they're so simple, it actually makes a lot of the proofs easier. And they're actually, so remember how I said earlier that they're mostly focused on the activation functions people are using. This would be the function that they're focusing on. This is the one that usually people are trying to prove stuff about now. And honestly, if I was an analysis person, this is a pretty nice function. Like, I mean, compared to all the other ones you can come up with,
It's not differentiable.
it's almost differentiable, except for one spot. So anyway, we're going to define our neural network. We're going to keep going through and define the forward propagation.
Is there a way to change the font size of comments in the Jupyter Notebook?
You want your comments to be bigger?
Yes.
I don't think so, but you can make it just a markdown thing. And then you can make that as big as you want.
How? I'm not very.
That's okay. So markdown, so you have your normal text.
Yep.
That's how it renders when you shift enter it.
Yep.
And then,
Whoa.
and that's just a pound, and you can add multiple pounds to change the size of it.
Fancy. That is
So that should be
awesome.
useful.
That is perfect.
Okay, cool. So now, this looks like a good old neural network. Let's instantiate it.
Are we doing nothing on the output layer?
What'd you say?
What are we doing on the output layer? We're not doing like a softmax or something.
So we are going to do a softmax. So this is actually a cool feature about PyTorch that is unique to PyTorch, but it actually implements a super efficient softmax calculation.
Right, that's right. And the
using
update.
the log softmax.
Yeah, that's right.
And so you can directly optimize the linear output, and then you can just apply softmax later. That's more information that you guys don't know yet, but it is cool though. So let me know when you guys are all caught up.
Mm-hmm.
So we're calling our class, and why are we inputting 4?
That's the number of classes, remember? So if you remember, we had K was our number of classes up here.
Yeah.
So we're going to input K as our number of classes, the number of classes that we want to predict. So, so I guess I kind of like talked a little bit about the softmax, so I might as well explain to you the softmax really quick. Because Justin brought it up. Okay, so the softmax function, so you see right here that we have an output of K in the reals, but that is in fact absolutely terrible for deciding which one of these that belongs to. And so the way we're going to deal with it, we're going to say that each of the outputs is a value that is, I wouldn't even say proportional to, but we're going to say each of the output in R is a part of a class, and then we want the value to be maximized for the correct class. So compared to the others, the maximum value, the maximum index of like, so like, let's say it comes out with, well, I'll just do this.
So you forgot to return X on forward.
Oh, you are correct. Yes, you are correct. Thank you. So, Justin, thank you for watching over me from afar.
Not that far.
So let's say this is the output of our network. And the correct class, let's say, is the 4th index, right? So it's the 11. So we want, the way that we're going to define something as being classified into the kth class is it's the maximum value. Now, there's a problem with this in that we need things to be pretty much differentiable. when we do this type of stuff. I'm not going to go too deep into it, but most of what we do with the neural network stuff must be differentiable. And even though the ReLU's like not entirely differentiable, we can at least define a derivative that makes sense for it, right? We can just define what domains take on what values in the derivative. And even if it's not a proper function, if it doesn't properly handle everything, it's differentiable at any single point. It has a value for the derivative at every point when we evaluate it. So that's enough for us to say that it's differentiable in a computer science context. But the max is it's very much not differentiable. There's not really a way that you can take the normal max and define it as differentiable. And so what we do instead is we come up with this function that looks like this. So let me just come up with a new. So we're going to define a function. So this is for the ith element in K. So like basically the kth element or the ith element of this array. We want to define the softmax function over the full array for the ith value. And so the way we're going to do that is we're going to pretend that this is approximately a probability distribution. Discrete probability distribution. And so we're going to say softmax is a very gross expression that I wrote using cool Python stuff. I'll explain to you in a second. So essentially the idea of this softmax is that we want the value of the correct class, the predicted class. So in this case, it would be the fourth index, to be much bigger than the rest when we look at it, because we want only the max one to have a value and the rest of them to be as close to 0 as possible. It's like an indicator random variable almost for each of these indices. You guys got that?
Yeah, I think so.
Okay, cool. So what we can do is, because we want it to be much larger, but we still want to be able to normalize it into being approximately this probability distribution idea that we had, so that it would be bounded, it would be on some bounded interval, and then we could pretend like it's an indicator random variable that says 1 if it is a class and 0 if it's not. We're going to do this implementation where we make each of them exponential, and this is the biggest one will be exponentially larger than the others. And so we add up the sum of all of them, and so the probability of any individual one is the exponential of the 1, so the exponential of the 1 variable, like we do here, divided by the sum of the exponentials over all of them. And also I should let you know, this is a cool thing in Python called a list comprehension. So when we want to write a simple for loop, but we don't want to take up multiple lines for it, we can do this thing called a list comprehension, where we can say for I in range whatever. So I will just say for I in X, for like we said before from our example, I just want the xith element, right? And so what this is saying is that I want a for loop where the value that I'm iterating over is the x, so like in this one would be softmax example x. And then I want to take, for each of the values in this array, I want to do something to that. And so what we can do is we can be like, I'm going to square it, and then I hit enter, and then I get back a list, which is what arrays are in Python, a list that has each of those values, each of the values that I put here on the left modified. And so you see we have the squared array by doing this. And This is called a list comprehension. It's a cool little feature in Python that I probably use way too much. But it lets us write these concise expressions such as this. And feasibly, it could be parallelized, but it usually isn't. Usually it's just replaced by a for loop.
They have the same sort of thing in Julia.
They do. And that one is probably actually parallelized. So
Yeah, actually, I think in the Julia documentation they say to use
so
it.
that's where they got that idea from, actually, was the Python list comprehensions. So once everyone's all up to snuff, I'll just show you guys a quick
silly
example.
question. How did you get your nice little markdown thing to center like that? Oh,
Question.
you just did alignment. I see. Yeah, that's fine.
You can use $2 signs as well, I think.
Oh, really?
Yeah.
Wait, how do you make one of those markdown things?
Oh, you just
Oh,
so
yeah,
you,
yeah, that's nice. It
you make
works.
a new box, Quentin, and
Yes.
you go up to wherever it says code and switch it to markdown. And then you can also, like Justin was saying earlier, you can make a new one, click the box number, and then hit M on your keyboard, and it transforms it into markdown.
And it's just the tech.
I mean,
Pretty much.
it's LaTeX mixed with a simpler markdown form, a simpler format called markdown.
Let's see.
So oftentimes it's easier than than LaTeX, but it does include all of the math stuff for LaTeX. So an example of what softmax looks like. Let's make a little figure here, just for shits and giggles. You guys don't have to write this down, but you can if you want. So let's just apply our softmax function on our example, softmax example X. Plot it out as a histogram. It's a little big. Let's bring it down to like 100. And so as you can see, the largest variable by far is the last index because it's the largest one, even though they're actually quite close. 11 and 10 are quite close in these two indices. It's more than, it's an order of magnitude larger. And so kind of the idea about this is now, instead of trying to like say, I want the maximum to be it, we can actually, now our output of our neural network, like we have here, can be any real value, because the exponential is defined for all real values. And so what it will just end up being is having this as our output, and thinking of it as a probability means that we can maximize, so we can optimize, which we'll eventually do, and we'll talk about further. But essentially what we're going to do is we're going to be able to say how good we did with a given hypothesis by how far apart this is from the distribution that looks like this, where all of the rest of them are small and only one of them is big. And all I did to change that is I changed the 10 up here to a 0.
Mm-hmm.
So that these are all much smaller because it's using an exponential. This is much larger than this, which means these are all very close to 0. And so this is approximately an indicator function for the maximum. And this would be the preferred output. We want the maximum one to be as close as to 1 as possible through the softmax, and it tells us this was the maximum.
Can you say that again? So we want the maximum to be
So the softmax function is saying that it's telling me which one of these indices is the largest in a differentiable way. And we want the preferred output is that we want it to be as close to 1 as possible for the correct class or index.
I see.
And so, but it's able to do this with a wide range of real values, which significantly increases the possible ways that it could describe a certain situation.
So are we defining the softmax as it's like a discrete probability distribution over the classifications?
Yes.
Okay.
That is exactly what it is. And that's kind of what I was getting at. Is the idea is that it's like the probability. So what it's supposed to be, and I should warn you that treating this as a probability explicitly, like the outputs of a neural network classifier as a probability explicitly, will disappoint you. So it is, so we're modeling it as a probability distribution. You're right about that, Quentin. But the problem is that you can have, so yeah, basically what I was saying is that this can make a prediction of 1, or very, very close to 1, of there's a probability that it is class, the 4th class. But in the actual, like, in like the true distribution, when we think of it as like the x to expected y distribution, it is extraordinarily unlikely that the true probability is 1. Because that would mean that it never makes a mistake, and almost all classifiers will make a mistake eventually. Like if you have some input well defined for that, it will make a mistake. And so it is, but it will still predict with high confidence, even though it's completely wrong. Does that make sense?
Yeah.
So that's the reason, like, be worried about thinking of it directly as a probability distribution, but we're nonetheless going to treat it as though it's a probability distribution for the purposes of all of our building of these, all of the definitions, all of the creation. But in practice, you want to avoid thinking about it as a probability distribution. Another little note is that this is extraordinarily unstable numerically for large values of x. And so you will run into problems with that. And for that reason, that was something I was talking to Justin about earlier, is that most of these neural network libraries will instead define this as a log softmax, which then is much easier to describe. And there's ways that you can solve it much more efficiently without being totally hosed. So the other thing that you might want to note about that is if you like probability or statistics or anything like that, this ends up having the intuitive explanation of being the negative log, so if you take the negative of that, it becomes the negative log likelihood estimate of a class. And so that's kind of cool. But we won't have to do any of that ourselves, because PyTorch will do it for us. People smarter than us solve these problems for us, and for that reason, we're going to get rid of all of this code.
What?
Did you have it written down?
Yes.
Well, you can keep it. You can keep it. But I'm just saying that's just so that you understand what it is.
Okay.
But it's going to be baked in here. We're not going to have to even define the softmax at the end. Technically, you should be like something like, if you want to get an output like that, but we're not going to actually have to do any of that. So now we get to talk about the learning part, which is arguably more fun than what we've been doing so far. So let's see, where are we? I'll just make a little separation. The learning part. So, at every step,
we can. Oh,
what's up? Okay, so at every step,
yep.
We chose differentiable functions, or nearly differentiable in the case of the ReLU. And the reason why was so that we could make some huge sweeping assumptions, which is always the best kind of math. So like I said, this is kind of where neural networks go off the rails of making any sense mathematically. But it empirically works, and that usually is good enough. So we're going to talk about finding, so we want to go back to that problem from before of finding a set of parameters which correctly approximates the oracle function. And so I'll quickly like give like the form, I'll rewrite down what we had said about the ReLU before, the loss function before. Loss function is some function from L to H, A to X to R. This is the correct one. I was struggling to write it down earlier. Well, that's not how you do it. So that's my macro for it. So the loss function takes in some state space, and assuming we have the oracle function, this also gives us the f, right? The y for a given x. And so this is our hypothesis. And so this is our loss function, which says that given a hypothesis, this is how well we're doing. This is the true loss function. And so this is going to be our error metric. And as long as we pick our error metric to also be differentiable, then we can assume that because we made the assumption earlier that our training set was realizations of the true distributions, that would be equivalent to saying those are realizations. That is what the oracle would have said for that input. Correct? And so if y equals the oracle function of x, then we can just assume that the training set can be substituted for those outputs. And so assuming, again, that this is a sufficient number of points to represent the distribution, our loss function is fully differentiable all the way back to the inputs, where it would be like L of, let me write this down for you guys. So then what that would be like is like our loss function takes in our hypothesis, call it H, and a training pair. And it's able to tell us how well we did. That is terrible. There we go. So we input our hypothesis, which is our model that we've constructed so far, our neural network, and our input pairs. And this is sufficiently good, as I said, to pretend like we know the oracle. And these XY values are just constants. They don't end up playing into the it being differentiable or not. So we don't have to care if the oracle function was differentiable. And so the way that we can deal with this now is that L, this ends up being looking like L of H of X and then some Y, right? When we call this function, we call our loss function. Because we have our, like when we actually implement this, it's going to be the output of our hypothesis and the correct value. And we're going to give some value and how well we did on that, as long as it's, again, as long as it's differentiable. We can propagate, we can use the chain rule to say that this is equal to L prime H X. I'm doing this off the top of my head, so feel free to correct me if I get anything wrong. H prime of X. But then we know that our hypothesis is a succession of composed differentiable functions, which means that we can define it again. We can go further with this, and we can, like, let's just say the subscript on H is the layer, right? So this would be like layer 3, layer 2, and then we would have H of 2, X prime, And so as you can see, we can kind of recursively go back, you know, for each layer all the way back until we get to the final x, the final input. And so because of all of our functions are differentiable, we can actually write a closed form expression for what the derivative of the loss function is at any point, given a training, an element of the training set. And so if we assume that if we assume that computing the gradient of this for any given xy is kind of like saying that that's the gradient of the true distribution at any point, and we assume that if we were to follow the contours of the loss landscape, we would we would eventually reach a local minimum, which results in a classifier, which is maybe not epsilon good, but kind of maybe pretty good. And this is kind of the image is not defined. Where is this? Where did I put my image? I deleted it. Okay, hold on. Never did on this. You don't need this, but I do. So that I can show images. So this is a gigantic photo of this process, which would be given an x, so given an xy pair, we find the gradient at a certain point, and it gives us an estimate. So at this point, this is the gradient, and then we take some step along in the direction of the negative grade. Well, the true gradient would be going up, but we want to minimize our loss function. So we're going to take some step along the negative gradient. Then we're going to assume that we're in a new place in parameter space. And then we're going to use our new hypothesis, using our new parameters that we got from updating the parameters using the gradient, to evaluate a new piece of the training set. And then we can follow this iteratively until we reach, hopefully, a good model.
This is effectively Newton's method.
So I don't remember. If I don't recall the specifics of Newton's method, can you remind me of it?
Newton's method is a gradient descent.
Oh, then yes, it's Newton's method. But we do have a problem here. So far, we've assumed that we actually know the true gradient, and this is actually probably false. You would have to have, so the normal way that people think about this, if it was to be Newton's method, is you would, or even close to it, is we would evaluate the gradient by taking the mean negative gradient over all images to make one step. Right? Because the only way that would be representative of the distribution is to evaluate every single training pair in the training set, and then take the average to find out what our expected gradient at a certain spot is. This becomes a problem if our data set's very large and the distribution is very complex. We would need to take, we probably need to take a huge number of steps to get to a good model in a high dimensional parameter space. And, oh, can you guys still hear me? It keeps telling me my internet connection is unstable.
I can hear you.
Okay, cool. So it would take an enormous amount of time to be able to solve this problem. So what we do instead is we come up with this idea that we're going to approximate the gradient locally of the loss landscape over a subset of the training set, known as a mini batch. And so we do the same thing where we would with what Quentin was talking about for normal gradient descent, of taking the mean loss gradient. We do it over a very small subset of the total training set. And we'll just assume that, let's say, for example, maybe we take 100 examples from our training set, right? And we'll assume that they're IID, independent, identically distributed in the distribution of images, for example. And we compute the gradient over each of them, take the mean, and then we take a step in that direction. And this is approximately almost as good as the gradient descent that we talked about before, but it's way less expensive. We can take many more steps because each of these x's now, instead of being the full set of training images, is now just, or training points, is now just a couple, like maybe like 50, 40 maybe even. And so even if we take, this gives us the chance of randomly taking a wrong direction step, but on average, we're going to be going the same direction as as evaluating the whole set, but we're going to be able to do it much, much quicker. Does that make sense? This is called stochastic gradient descent. Does that make sense to everyone?
Mm-hmm.
Yeah.
Okay, cool. Are you with me? Are you not with me?
I think I'm with.
That's Sajit, in case anyone doesn't know. But anyway, so this is a powerful optimization tool to train models. It was really the first optimization method in deep learning. And you can kind of imagine that there's going to be a lot of evaluations of this. And while it's not extremely computationally expensive, it's certainly not cheap. And so this is the reason why people stopped looking at neural networks in the 80s and quit until GPUs were invented. Because GPUs can do a lot of these operations in parallel quite quickly. What's up, Quentin? Did you say something?
No.
Okay. So there are some problems with this though. So stochastic gradient descent is the basis optimization that most people use, but it's not the best generally. There is no, I would like to preface, but there is no best optimization algorithm for this type of stuff, but stochastic gradient descent is probably not it if there was one. So let's come up with a couple problems with it off the top of our heads. What if we reach a saddle point? We're going to bounce around along the saddle point for a really long time. We have no way, and we also have no way of quantifying if we're at a saddle point, so it could look like we're actually in the right spot, where we've trained a good model, when actually there's much better models all around us. And actually this ends up being a problem they've found empirically. Again, this is great with all the empiricism in this field, but empirically, high dimensional distribution spaces like what we're looking at, such as images, for example, or text, generally they have a lot of saddle points. In fact, saddle points far outnumber the minima, it appears. And so we can add some things to this. So what if instead, so one idea that we do to solve the saddle point problem, for example, something called momentum. And so we think of, instead of these negative gradients being the actual step direction, what if we think of that as an acceleration term? And then so we can accumulate a velocity over many steps of the direction we want to go in. And this feasibly could actually handle a lot of our problems with stochasticity as well. Because we're going to, on average, instead of shooting out, it's going to add an acceleration in this direction, acceleration in this direction, and then the total movement is going to be along this line. And then you're going to know that you should probably keep going in this direction until you get more updates that tell you to change your direction. Does that make sense?
Yeah, it seems like that would take longer to converge.
So that's why I have a very pretty picture. This is a collection of different optimization algorithms. And so the reason the momentum does better is because even though it goes off in a little bit of the wrong direction, it can speed up the size of the step that it takes. Because it doesn't just take cues from the direction of the velocity, but also the size of the step it should take. So can you guys see this pretty well?
Mm-hmm.
So momentum is the green one and SGD is the red one. SGD has a constant velocity because it's just picking a direction based on where it's trying to go. Momentum can speed up and also slow down, but you can also see it as this problem with overshooting the solution if you see. So as you can see, these are not the only two solutions to this problem. There's a lot of different optimization problems. Optimization algorithms for this type of stuff. I'm not going to go into most, if not almost none of them, because this is not really where you want to focus your time if you're just getting into deep learning. For the most part, and this is also something that will piss off a lot of people to say, but there's a couple of go-to optimizers, and for me, those go-to optimizers are ADAM, which is an adaptive learning rate mixture of a few different optimizers, including momentum and a few other things, including the Adagrad that's on this image. ADAM is my personal favorite. And then SGD with momentum is another go-to optimizer. And those are in general for deep learning practitioners, people just sitting down to solve a problem. Those are the two that most people will go to. The reason I say most people is that what the people who have worked on this for a long time, what you find is that generally what ends up being a much better predictor of your success with a given optimizer is not that one optimizer is better than another. It ends up being your experience with a given optimizer. So if you have played around with SGD with momentum for a really long time and you've gotten used to playing with it on a project, you will probably, over a collection of projects, you will probably just get better results with SGD with momentum because you'll be better at tuning it, better at seeing the problems when its problems are cropping up and how to solve those problems. And so that pisses off a lot of people to say, but honestly, like each of them has a number of knobs to turn. And the one that works best is the ones you have the most experience turning knobs on. With that said, I probably wouldn't use basic SGD. It takes forever to converge on a lot of problems, but it's your life. You can spend it however you want. If training neural nets is when you want it to be a bigger part of your life than it has to be, then you should use SGD. Another problem with the optimization model we have is, like I said earlier, is you need to have a training sets which pretty much representative of the true distribution. If it's not representative, like it's highly skewed in one direction towards maybe one class in our classification example, there's not really always a clear solution to solving it. Usually the answer is more data. But that won't always work if there's one class that outperforms all the others. Like if there's, like for example, let's imagine that in our data set, what if for every one yellow point, there was 1 million blue points? And then there's one of this one and then one of this one. For an optimized model, a very simple model that works very well for the model to optimize its estimation on average is to just always pick blue. Because most of the time it is blue. But then it's not actually learning anything of interest. And this can also happen if most of your training set is blue, but the true distribution looks something like this, then it will make the same mistake. So you can fix problems like that by like making sure your data set isn't skewed. Actually, Justin actually had to do a project where he had skewed data with rare events and stuff. I don't even know if he can hear me right now, but
yeah. Yeah. It's a big problem though. But yeah, basically it's like you can fix it using either you tweak the loss function to penalize predicting wrong stuff. Assuming if you have like that big of a class disparity, you obviously kind of want to predict those rare events, but yeah, you can either penalize the loss function for mispredicting, the important events but rare events a lot, or you can change the way your data, the distribution of your training data, by basically repeating examples of your underrepresented classes.
Yeah, and they generally call that importance sampling. So that's one problem that you'll probably run into if you try and apply this. And so I obviously I keep like talking down about deep learning. I think I should probably preface that. I have not been, in this talk so far, I have not been a very positive person for deep learning. I'm usually talking about its problems. And it's mostly because I want to make sure to damper your expectations when you try this yourself, because it will almost certainly not work the first time that you make your own model for a problem that you're really passionate about. And then you're going to be like, I guess I'm bad at neural networks. No, neural networks are bad, but they can solve really hard problems. And when these techniques do work, they often work very effectively. So we're going to use them to solve our classification problem from above. As I was saying, so we're going to define our loss function finally, because McKenna's been asking for that for a while. And so we're going to do, it's important that you know the other things first. So we're going to do something called the cross entropy loss. But for the type of problem that we're doing, it ends up just being the negative log loss of the true value. So it ends up being negative log of h of x for the specific class minus the true probability, which is 1. And so basically you want this to go to 1. So you want to maximize this probability. Well, so you want to maximize this probability, which means minimizing this expression. So when this expression is 0, the probability of the correct class being true is 1 in our softmax. Does that make sense?
Yeah.
McKenna, does that make sense?
I think so.
Okay, cool. So there's the fancier name for that is cross entropy loss, and there's a lot of, you can write down the full expression. There's a larger expression for it, but as long as you're only predicting one class, it's much simpler. Cross entropy loss is more generally can be used to fit discrete distributions to one another. But for this case of just having one true y and the rest of them 0, it just ends up being that negative log loss. So yeah. One thing, so like I was saying earlier, when you have something like PyTorch, most everything, someone else has already solved the hard problems for you. And so instead of having to write all of these hard optimization algorithms, we're just going to do import torch.optim as optim. And this contains all the optimization stuff that we're going to need to be able to solve these problems. So to get our negative loss, our negative log likelihood, we're going to define the loss function. It's equal to nm.cross entropy loss. And then our optimizer, we're just going to use stochastic gradient descent. Even though I said don't use it, we're going to use it anyway. Because it's a good starter example. We're going to define a learning rate, which is which kind of tells us how large of a step should we take at each gradient update, at each gradient approximation, is the learning rate. That should not be a minus, that should be an equals. And because we want to use SGD with momentum, we're going to talk about a decay term. So this momentum is how much should the velocity decay at each step, because we're continuously adding acceleration, but we don't want it to blow up with infinite acceleration. So we're going to slowly decay the velocity term of the momentum. And so we get rid of 10% of the momentum at every step. And then the last parameter we're going to pass to our optimizer, something called weight decay. And if you're wondering how I'm coming up with these numbers, I'm pulling them out of my butt. So these are called hyperparameters. They're just numbers that you set ahead of time to be able to control your optimization. It's also the number of parameters you have. It's basically all the knobs you have to turn to make your model do better or worse. And there are like entire papers on automatically tuning hyperparameters, and some of them are super good, but we're not going to talk about any of those ideas because it's pretty hard. I mean, because the actual hyperparameter tuning is like a black box optimization problem, and it's pretty hard to be able to actually talk about it, but they do have hyperparameter search ideas. So this weight decay term is what's called a regularization term, which we're going to add to our loss function. And what this says is we want to penalize the network. We know that computers are bad at dealing with really big numbers. And we have no way of telling it so far that we don't want it to pick really big numbers to make it numerically unstable. And so what we're going to do is this regularization term says that I want to penalize you for picking big weights. When you pick a big weight or a big bias, I'm going to penalize you for it. So if you pick it, if you're the optimizer and you think that we should have a bigger value, you can, but on the whole, we want to not do that. And that way we should usually stay within numerical stable regimes for the matrix multiplication and everything. And so basically we're saying that like we're going to sum up the squared weight, all the squared weights, multiply it by this hyperparameter, and add that to our loss error. So we're going to penalize it quite heavily. And so yeah, if you were to make this yourself, you'd have to fiddle with these to get it to actually train correctly. But luckily I did this ahead of time, so I already know that these work, hopefully. So now we're going to make a quick little function to plot our estimation. I did do, hold on a second, let me just double check that I have that imported. Did you guys ever import the camera?
No.
Okay, we'll do that really quick. So you're going to want to import this from celluloid, import camera. You probably don't have it installed.
I've never used that package before.
What'd you say?
I've never used that package before.
Oh, you're going to love this. You know how matplotlib animations are terrible?
Sure.
Well, this just lets you take a picture of the plot and then update it.
Oh, that's cool.
So how do I go about getting?
So to get it, go create a new cell, type exclamation mark, and this is telling it we want it from the command line. Pip install celluloid, shift enter. And we'll go through the whole downloading of this. Let me know when you guys are good.
Good.
I'm still waiting, but you could probably go ahead. I can catch up.
Okay. So once you have that, you can shift enter and import your celluloid. Because of this, because we did the auto reload thing, you're just going to be able to import the camera from the new package. So McKenna, did that work for you?
Yep.
Okay, cool. So let's define this visualizer. I'm bound to write the mistake in this, by the way. And in case you're wondering, this is just, none of this is really important to know. It's just a bunch of Python. So, and you can note if you want it, but.
Is that how you spell a range?
What did you say?
Oh, a range, not a range.
Array. Quentin, how you doing over there, man?
Oh, I'm catching up. It's a good thing I kind of pointed that out because I definitely would have spelled it arrange. Been trying to
Is
figure out
a
why.
range.
Yeah, trying to figure out why it didn't work.
Why didn't what work?
Well, if I had spelt it like a range, like I think, like you know the word.
Yeah. All right, that was fun. And so when you get that all to work, you should be able to run it. And mine didn't work. Where did okay, y is not defined. I see. This should be capital Y. There we go.
Can you go? I'm still.
So
No
wait,
problem.
oh yeah, the same. Case y.
So let me know when you guys are all caught up and we'll show you the final product. It's going to be our neural network's fantastic starting classification of this space with no training. While Quentin's getting this sorted out, I'm not going to leave you behind, but I am going to get through this little part.
Yes.
So, as you can see, this is doing really poorly. classifying the points. My other example of this, I'll show you really quick, looks like this.
Yeah, mine looks kind of funky. Yeah, like that.
And so this is just because our neural network is currently a random hypothesis. And there's no reason to think that our hypothesis should be anywhere near the correct hypothesis or any correct hypotheses. Mine is extremely bad. Mine thinks all of this is orange.
Lecture back on track.
Cool. You all good? You got your
Yeah.
your
All
bad
good.
classifier?
Yep, figured it out.
Sweet. So now we're going to do some more coding. So there's something in PyTorch, what they call a data set. So like obviously we know what a data set is intuitively, but basically you want to create a class that encapsulates your data set so that it's accessible in a really canonical way. So you can use some cool tools on it. So we're going to do that next. So we're going to import this data set from the Torch utils. So you're going to see this is actually really similar to what we had before. When we were generating the initial, what we'll call our test set, we're not going to let our neural network ever see our previous test set because we don't want it to know what it's going to see at test time and bias it.
Should that be capital Y?
Yes, thank you. It's because I switched over because it looked better when we were typing, but that's what I did previously. This is exactly like what we did last time. We're going to do the same same stuff. You can probably even almost copy parts of this from the previous one. I'm just typing it for completion. And so what I'm doing now, just so you guys know, this len function, this is, so when you, in Python, if I have an array, I can say len 1, 2, 3. And it'll tell me there are 3 elements in this array, the length of the array. But actually we can implement this for any class by defining this underscore underscore len underscore underscore that returns a number. Then we're also going to define, so when you have a class like you define something like this, you can access an element of it just by using these brackets, which is pretty similar to most programming languages. But we can actually define that as well with this get item. All right, that was incorrect. What's wrong? Why? Oh, I didn't. This should be a capital L in data loader, by the way. I miswrote that. So what's happening down here is that we're going to return a tuple of torch tensors, the first one of type float, second one of type long, where the first tensor is the input x vector, and the second one, the input, is the class. And this is a long, this is an integer. Tell me you guys are all ready.
I'm ready.
You're both good?
Mm-hmm.
All right, so let's test that it worked. And then we can access an element, like I said. We'll access the 0th element, and this is what you should get probably.
Oh no. Bad. Oh, that would probably do it.
I'm sorry to throw you through the fire like this, Quentin.
I've got it.
Did it work?
I'm not the last one this time.
So this is pretty cool. We're approximately getting, and while McKenna fixes hers up, we're approximately getting our XY pair from our training set, or whatever set it is. We're able to access the ith element of our data set, the ith pairs of our data set, and we get the input and the expected output. And so, or the oracle output, one might say. And these are both tensors, like I said before, because everything PyTorch deals with is a tensor. So this actually is kind of important to know how to put one of these together, specifically if you want to do your own data. Once you have one of these dataset classes, you can use it pretty transparently, like as if it was any other data set in your code. So a lot of this code is transferable, but the data set is emphatically not transferable between problems. Now we have a data set. We're going to use that other thing, the data loader. Super useful. Do you remember how we said that we were going to make assumptions that the draws from the training set were IID, independent identical, and we wanted to grab them in groups? Mini batches is what we called them. Well, we can do that extremely easy with this. We're saying I want a batch size of 10. I want to shuffle my data because it's not already shuffled, so that all of my draws are approximately independent, identically distributed. And I just pass in my data set. And now I have a data loader. And this data loader makes it pretty easy. It's something that you can enumerate over, which is what the next thing we'll do, so we can finally start training. So now, excitingly, we can finally bring all of what we've learned together to put everything together to actually train a neural network to solve this problem. I know that was a lot, but you know now, so you're welcome. So we're also going to make a cool visualization because I think that's fun whenever I make code. Make a figure, use this cool camera. The camera that we downloaded. And so we're going to choose a number of things called epochs. And epochs are what we call one full iteration through a data set. So our data set has some length. And so when our learning algorithm has looked at every element in the data set, we'll say that it's done with one epoch. And so we're going to need 15 epochs here because it's only 5,000, sorry, 5 times 4, so it's only 20,000 data points. This is a really small data set. So we're going to do 15 epochs over it. We're going to calculate the running loss, so the average loss over one epoch. And so we're going to for I data enumerate data loader. So this is saying for each element in the data loader, so each batch in the data loader, give me the data and give me the index. And so inputs labels equals data, which is what was passed in by the data loader. We're going to 0 we're going to 0 the gradient estimate from the network from the previous time it estimated a gradient. By calling a 0 grad function. We're then going to predict y given x. Using our network. We're going to calculate the loss using our loss function. We're going to do the chain rule, propagating back over each of the samples to calculate mean gradient. This is called the backwards pass. Similar to how we called it forward pass when we put the input in the network and we went through, that was the forward. This is the backward pass. Then we want to take a step. Take a step towards the mean negative gradient, the optimizer. Get some statistics.
Does that need to be an equal equal?
Yes. Thank you. So hopefully, if I wrote all this code correctly, it should be just that simple to train a neural network. Let's find out. So as you can see, if you look on my screen right now, this is the network training. So I'll scroll back up while this trains so you guys can finish typing it all out. Okay, so mine finished training. That's not bad.
Mm.
So now we're going to use our camera to make it cool. Cool GIF. I'll show you a cool little thing. Watch this. That's what training actually looks like.
That is very cool looking.
Oh,
Wait, can
It's
you-
working now.
What? Wait.
Yeah, I just had to rerun everything. Who knows why?
Maybe I'll try that too.
Check that out.